This is SpaceTime Series 26, Episode 15. Coming up on SpaceTime, the Milky Way found to be more unique than previously thought, Boeing Starliner Calypso ready to fly in April, and we look at some of the world's biggest magnets. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has found that the Milky Way galaxy is too big for its cosmological wall, something not yet seen in any other galaxy. The large-scale cosmic web-like structure of the universe is composed of filaments connecting nodes of gas, galaxies, and galaxy clusters, all surrounding vast near-empty voids. A cosmological wall is the flattened arrangement of galaxies that border on these voids. For some reason, the voids seem to squash galaxies together into a pancake-like shape, resulting in a flattened arrangement. The new findings, reported in the Journal of the Monthly Notices of the Royal Astronomical Society, suggest that the wall environment, in this case called the local sheet, influences how the Milky Way and other nearby galaxies rotate around their axes in a more organized way than if they were, say, in a random place in the universe without a nearby wall. Typically, galaxies located next to a cosmological wall are physically a lot smaller. But by comparison, the Milky Way is surprisingly massive, and that makes it a rare cosmic occurrence. The new findings are all based on state-of-the-art computer simulations. The study's authors simulated a volume of the universe of nearly 1 billion light-years across, a region containing millions of galaxies. And they found that only a handful, about 1/1,000,000th of all the galaxies in the simulation, were as unique as the Milky Way, meaning they were both embedded in the cosmological wall like the local sheet, and they were as massive as our own galaxy. The authors say the findings mean it may be necessary to take into account the special environment around the Milky Way when running future simulations in order to avoid a so-called Copernican bias in making scientific inferences from galaxies around us. This bias describes the successive removal of our special status in the nearly 500 years since the astronomer Copernicus first demoted the Earth from being at the center of the cosmos. Since then, this bias has described the successive removal of our special status, assuming that we reside in a completely average place in the universe. See, to simulate observations, especially on a cosmological scale, astronomers sometimes assume that any point in the universe in the simulation is as good as any other. But what the team's findings indicate is that it may be really important to use very precise locations when making such measurements. The study's lead author, Miguel Aragon from the National Autonomous University of Mexico, says the findings indicate that the Milky Way galaxy is different. He says the Earth's very obviously a special place because it's home to the only known life forms in the universe. But it's not the center of the universe, or even the center of the solar system. And the Sun is just an ordinary star among billions in the Milky Way galaxy. Even our galaxy seemed to be just one spiral galaxy among billions of other galaxies in the observable universe. The Milky Way doesn't have a particularly special mass or type. There are lots of spiral galaxies that look very similar to it. But now we know it becomes rare once you take into account its surroundings. If you could see the nearest dozen or so large galaxies easily in the sky, you'd see that they all nearly lie on a ring embedded in the local sheet. That's a little bit special in itself. What the authors have discovered in their simulation is that other walls of galaxies in the universe, like the local sheet, very seldom have a galaxy inside them as massive as the Milky Way. Aragon says you might need to travel 500 million light-years from the Milky Way, past lots of galaxies, to find another cosmological wall and a galaxy that's the same as the Milky Way in comparison to its companions. And that's a couple of 100 times further away than the nearest large galaxy around us, Andromeda. This is SpaceTime. Still to come, Boeing Starliner Calypso ready to fly in April, and we look at the world's biggest magnets. All that and more still to come on SpaceTime. Boeing CST-100 Starliner Calypso is now expected to carry its first human crew to the International Space Station in April. The trouble-plagued program is years behind schedule, with software glitches coming close to destroying the spacecraft. Once operational, Starliner will join SpaceX's Dragon in transporting crew to the space station as part of NASA's Commercial Crew Program. The reusable capsule was mated to its new service module inside Boeing's Commercial Crew and Cargo Processing Facility at NASA's Kennedy Space Center in Florida last week. Next, the combined spacecraft will be integrated on top of the United Launch Alliance Atlas V rocket in coming weeks prior to final checkouts, and then its rollout to Space Launch Complex 41 at the Cape Canaveral Space Force Station in Florida. NASA and Boeing recently completed a full start-to-finish mission dress rehearsal for the crew flight test. The rehearsal took several days at Boeing's Avionics and Software Integration Lab in Houston, testing software and computer systems as well as crew systems along with operations teams. The all-important crew test flight follows 2 unmanned orbital test flights, the first of which in December 2019 was a total disaster. Problems began when the mission clock triggered an orbital insertion burn at the wrong altitude, and that caused the attitude control thrusters to consume more fuel than planned, leaving the spacecraft too low to reach the space station safely and forcing the mission to be aborted early. However, while they were orbiting the Earth waiting to return, 2 more software issues were uncovered, one of which would have prevented the spacecraft from docking to the space station anyway, but the other would have affected the thruster firing sequence needed to safely jettison the service module prior to the crew capsule re-entering the atmosphere. Instead of maneuvering the service module away from the capsule, it would have caused it to collide into the capsule, destroying both spacecraft. Luckily, the issue was rectified before re-entry, and the spacecraft did eventually land safely at the White Sands Missile Range in New Mexico. A major mission review identified 80 issues which needed to be modified before another unmanned test flight could be held. By August 2021, Boeing were ready to try again. But further delays and bad weather somehow caused moisture to interact with the propellant, triggering corrosion in 13 propulsion system valves in the service module. Attempts to repair these on the launch pad were unsuccessful, and it was decided to return the launch vehicle to the assembly building and then strip down the spacecraft to better access the issue. However, the problem was so bad, Boeing eventually decided to replace the entire service module, further delaying the test flight. The Orbital Flight Test 2 mission finally launched on May 19, 2022, docking with the space station on May 22nd. And the rest of the mission also went smoothly, including a perfect touchdown at White Sands. Now it's time to get people on board. Starliner is compatible with the Atlas V rocket, as well as the Delta IV, Falcon 9, and the future Vulcan Centaur launch vehicle. The Delta IV has now been retired, and the Atlas V will retire next year. The United Launch Alliance says they've allocated 7 Atlas V boosters for Starliner missions. That's enough for the upcoming crew test flight, as well as 6 operational missions. After that, Starliner will transfer to Vulcan Centaur boosters instead. This is SpaceTime. Still to come, we look at the world's biggest magnets, and later in the science report, does your dog understand your intentions? We'll find out. All that and more still to come on SpaceTime. One of the world's most powerful magnets is slowly being assembled at the heart of ITER, the International Thermonuclear Experimental Reactor, the world's largest fusion reactor project now being constructed in southern France. Sustained nuclear fusion could open the door to unlimited renewable energy, slashing carbon emissions and pretty well ending climate change. Estimated to cost over $150 billion, the project's described as the most expensive scientific experiment of all time. It dwarfs the Square Kilometre Array project now being built in Australia and South Africa. It's bigger than the Large Hadron Collider. It'll be the most complicated engineering project in human history, and one of the most ambitious human collaborations since the development of the International Space Station. When it goes online sometime around 2027, ITER's massive reactor will fuse hydrogen isotopes to deuterium and tritium plasma in a special magnetic donut-shaped vacuum chamber called tokamak. The tokamak will heat the plasma to over 150 million degrees Celsius. That's 10 times hotter than the core of the Sun. At this temperature, the plasma will undergo fusion, giving off large amounts of energy which can then be used to create electricity by heating water and creating steam to spin turbines. The ultimate aim is to produce 10 times more energy than what's needed to power the system. ITER's thermonuclear fusion reactor will use over 300 megawatts of electrical power to cause the plasma to absorb 50 megawatts of thermal power, creating 500 megawatts of heat from fusion for periods of between 400 and 600 seconds. At the heart of the facility will be the world's largest magnet, known as the central solenoid. When fully assembled, the central solenoid will be 18 metres tall and some 4.3 metres wide. It'll be capable of producing a magnetic field measuring 13 Tesla. That's around 280,000 times stronger than the Earth's magnetic field. In fact, it'll be strong enough to lift an aircraft carrier weighing 100,000 tons. Built by General Atomics, the central solenoid will be the largest and most powerful pulsed electromagnet ever constructed. It's actually made up of 6 individual solenoid modules, which will be stacked inside the center of the tokamak. The entire magnet will be as tall as a 4-story building and weigh roughly 1,000 tons. Each individual module is essentially a humongous coil containing around 5.6 kilometers of steel-jacketed niobium tin superconducting cable. Faraday's law of induction tells us that electricity passing through a wire generates a magnetic field perpendicular to the wire. When that wire is coiled into a circle, the electric current produces a circular magnetic field, and each coil amplifies the magnetic field strength. A solenoid is created by coiling a wire many times. The central solenoid will create powerful magnetic fields, physically pinning the superheated plasma in place and preventing it from touching and vaporizing the tokamak's walls. But as impressive as this all sounds, it isn't the biggest or most powerful magnet ever built. That honour goes to the National High Magnetic Field Laboratory, MagLab, which has just received over $195 million in funding from the National Science Foundation. MagLab's facilities are spread over 3 campuses, including Florida State University, the Los Alamos National Laboratory in New Mexico, and the University of Florida. Nearly 2,000 scientists from around the world use MagLab's facilities each year, undertaking groundbreaking research across multiple scientific disciplines in magnetic field research. These include condensed matter physics, biology, bioengineering, chemistry, geochemistry, biochemistry, material science, power generation, and environmental studies. To facilitate the research, MagLab has a wide array of different types and sizes of magnets, including some of the world's biggest and most powerful. Florida State's MagLab in Tallahassee currently holds the record for the world's most powerful magnet for nuclear magnetic resonance spectroscopy experiments. The 33-ton series-connected hybrid magnet set the record in a series of experiments in 2016, when the instrument reached its full field of 36 Tesla. Its sister facility at the Los Alamos National Laboratory in New Mexico hosts the Pulse Field Facility, which provides researchers with experimental capabilities for a wide range of experiments and measurements in non-destructive pulse fields up to 101 Tesla. Pulse field magnets create high magnetic fields, but only for fractions of a second. Power comes from a pulse power infrastructure, which includes a 1.43 megawatt motor generator and 5 64 megawatt power supplies. The 1,200-ton motor generator sits on a 4,800-ton inertia block, which rests on 60 springs to minimize earth tremors and is the centerpiece of the Pulse Field Laboratory. The facility's magnets also include a 60 Tesla long pulse magnet, which is the most powerful controlled pulse magnet in the world. It's all very impressive. This report from the National Science Foundation's Miles O'Brien.
That thrum you hear is the sound of science at work. It's coming from magnets, some of the most powerful in the world.
So we are indeed a world-class facility. There are many different kinds of magnets, superconducting magnets, big resistive electromagnets, pulsed magnets.
With support from the National Science Foundation, the National High Magnetic Field Laboratory, MagLab as it is called, is a mecca for groundbreaking research across scientific disciplines.
So I direct a very unique laboratory to bring high magnetic fields to researchers who come to our lab every year to study important research topics in the areas of materials, of energy, and of life.
The magnets here are of a different kind altogether, millions of times more powerful than anything you would stick on your fridge.
You should think of a high field magnet, a powerful magnet, as a research tool, much like a high-powered laser is being used by scientists, much like an atom smasher. We're a research tool.
Analytical chemist Amy McKenna is a staff scientist working on the ion cyclotron resonance magnet. She's all about oil, how to refine it more efficiently, and how to better clean it up when it spills.
Every crude oil in the world is unique. It is a function of the temperature, the pressure, and the organisms that died and created that mixture.
Petroleum is what's called a complex mixture. Think on the order of 40,000 different chemical compounds in every drop.
We analyze the compounds in crude oils, in dissolved organic matter, in water, and we measure their mass very accurately.
To do it, this magnet functions as a highly precise molecular scale.
In order to measure molecular weight, you need these types of scales. And that's what we do here, is we measure a fundamental property of molecules very accurately, to 6 decimal places.
In another part of the Mag Lab, physicist Corey Dean is using the DC Field Facility to research the properties of a relatively newly isolated material called graphene. It's a flat sheet of carbon molecules laid out in a chicken wire-shaped pattern.
It's unique in almost every metric that you can define. It's been called the strongest material, it's the thinnest conductor, it has one of the best thermal transport properties.
It's so unusual, in fact, that physicists are still trying to figure out the basics of how it works.
One of the things that we want to know is when we put this device in the presence of a very large magnetic field, combined with very low temperatures, both of these things are critical. Can we access what we call the quantum properties of this material?
That level of understanding is needed before engineers can really start making things out of graphene.
We can discover, for example, new electronic behaviors, which to a physicist might be very interesting, but to an engineer means that you can design a brand new material that maybe solves a problem that is facing challenges for like how to make a better computer, for example.
Dean is one of nearly 2,000 scientists from institutions around the world who use the MagLab facilities every year. Magnetic field testing can benefit many fields of research, petroleum and materials for sure, but also human health and medicine, batteries, biofuels, and much more.
So we know how to bring in newcomers to high magnetic field research, help to make their experiments successful so they can then publish their results and get the information they're seeking.
Visiting scientists don't even need to have experience working with magnets. All they need to bring is a worthy project. Experts like Amy McKenna are on hand to help.
That's the crux of a successful user facility. You've got to have the magnets, you've got to have the instrumentation, but most of all, you've got to have the talented people.
Putting the power of high magnetic fields to work, breaking through the boundaries of scientific knowledge.
And in that report by the National Science Foundation's Miles O'Brien, we heard from National High Magnetic Field Laboratory Director Greg Bobinga, ion cyclotron resonance facility scientist Amy McKenna, and Corey Dean from the Dean Lab in Experimental Condensed Matter Physics at Columbia University. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study suggests that people with schizophrenia may have abnormal activity in 12-hour cyclic genes. The findings, reported in the journal PLOS Biology, are based on evidence of 12-hour cycles in gene activity in the human brain, and signs that some of these 12-hour cycles are either missing or altered in the brains of schizophrenic people. Researchers searched for 12-hour rhythms in gene activity in the brains of people who were recently deceased, focusing on areas of the brain associated with abnormalities normally seen in people with schizophrenia. They found gene activity levels related to building connections between neurons tended to peak in the afternoon or night, while those related to mitochondrial function and therefore cellular energy supply tended to peak in the morning and evening. But this wasn't the case for people with schizophrenia. The brains of people with schizophrenia had fewer genes with 12-hour activity cycles, and genes related to neural connections were missing entirely. They also found that the genes that were present didn't reach peak activity at the normal times. The authors say further studies are now required to determine if these abnormal rhythms underlie behavioural abnormalities in people with schizophrenia or whether they result from medications, nicotine use or sleep disturbances. The publishers of some of the world's leading scientific journals have formally banned ChatGPT from authoring scientific papers. The artificial intelligence chatbot ChatGPT has so far been listed as a co-author on 4 papers and preprints. The decision to ban AI authorship is based on the simple fact that chatbots can't take responsibility for a paper's content or integrity. Some publishers say that chatbots' use, however, should be documented in the methods or acknowledgements section, and that not doing so could be considered plagiarism. Does your puppy dog understand your intentions? Well, a new study suggests that they probably do, at least to some extent. The findings, reported in the Journal of the Royal Society B, are based on tests to see whether dogs were able to distinguish if people were unwilling or unable to give them treats. During the study, dogs encountered a human who would regularly give them treats. But sometimes the food transfer failed, either because the human acted as if she was unwilling by pulling back on the treat in a teasing manner, or because she was unable by clumsily dropping the treat instead. The authors computer analysed the dog's reactions, finding that dogs tended to react more impatiently to actions signalling unwillingness rather than those signalling an inability. Scientists have confirmed that despite the claims commonly appearing on social media and made by some conspiracy theorists, the flu is not more deadly than COVID-19. David Muscatello, Associate Professor in Infectious Diseases Epidemiology at the University of New South Wales, says COVID has never had a survival rate greater than the flu. Meanwhile, Alan Cheng, Professor of Infectious Diseases Epidemiology at Monash University, also says the claim was false and that COVID always had a higher mortality rate than influenza, except for very young children. Claims that the figures included people dying with COVID as opposed to those dying of COVID are also untrue. Tim Mendham from Australian Skeptics says the first 6 months of last year alone saw COVID kill 27 times more people than the flu.
The fact-checking shows that COVID is more deadly than the flu. Surprise, surprise. Yeah, all the people who in the early days of COVID were saying, it's just bad flu, is wrong, because the numbers bear out that the impact of COVID is far, far worse than the impact of the flu. Just in the first 6 months of 2022 in Australia, there were 6,651 COVID deaths compared to 252 flu deaths. Part of that might be that you could say almost that people aren't being tested for flu at this stage because they're all being tested for COVID. But a death is a death, and if you know the reason for the death, then that shows that even in a particularly severe flu season, which there was in a few years ago, 2017, I think, there was only 1,255 deaths due to influenza. So already the COVID number is 6 times that for the half a year. So the numbers just show pretty clearly, without any necessarily need to prevaricate on it, that the COVID is far, far more deadly than the flu. And it affects people who have been vaccinated and those who haven't been vaccinated, although the higher death rate is amongst the unvaccinated quite significantly. Someone was suggesting that about 40% of people who die of COVID are unvaccinated. Seeing as only of the adult population, only about 2 or 3% of people who have been unvaccinated, that indicates that the vaccination works pretty well. Not entirely perfectly, no vaccination does, but yes, the issue is that COVID is far more deadly than the flu, of multiples of deaths, and that the people who are unvaccinated are more inclined to die than those who are vaccinated.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.